welcome back to our lecture video today. The topic of today will be tune amplifier. So this will be an application lecture. I will try to move very quick on the math, so excuse me on that. But at the end of the lecture, I want you guys to understand how to design a tune amplifier circuit so that you can have you can just adjust some parameter in the tuning circuit, then you can get to your desired what's that called, you can get to your desired resonant frequency, your desired gain, and your desired bandwidth. And by maybe applying some variable components such as variable inductor or variable resistance or capacitance, you can actually vary those things like gain and resonant frequency and bandwidth as you wish to. So let's get to this. So today is an application lecture, so I'll try to make it more applicable to the practical things and try to skim through the math. So I hope you guys can enjoy this. First of all, let's look at these three items. What do they have in common? So all of them have some knob, right? They have some knob that you have to turn to tune the frequency to the correct one. Okay, for example, the radio, you want to tune in to the correct frequency for communication. The audio amplifier, you want to tune your music to the correct frequency that you want to have the effect on, or the radio amplifier. So all of them have, basically all of them inside has a tune amplifier. So the topic of today, we will see how can we design and how does tune amplifier works. So what is a tune amplifier? In simple language, we can define a tune amplifier as a mid-band amplifier. So you know, mid-band amplifier, it basically amplify with a gain at a certain frequency range, and also this mid-band amplifier is coupled with a tuning circuit. So this usually the mid-band amplifier, all of the central resonant frequency and corner frequency are pretty much fixed. But if you add in a tuning circuit, you can actually change some of the component. So you can maybe vary the capacitance or vary the inductance of some component inside this tuning circuit to control for the resonant frequency or the bandwidth of the amplifier. So in technical terms, and I give you an example here of a typical CE or common emitter amplifier, a mid-band amplifier with basically a tuning circuit that is coupled at the load. So definition is tune amplifier combine amplification and filtering. So as you can see in the gain plot in here, it amplify, but it also filter everything outside of the resonant frequency. The transfer characteristic looks like that of the usual amplifier, except high and low 3 dB frequency are very close together. So instead of a wide band pass, you can have a lower, a high bandwidth, you can have a lower bandwidth. They usually use RLC combination to filter. So filter out the low pass and the low frequency and the high frequency. And analysis is similar to usual mid-band amplifier analysis, except that we have a reactive load and other impedance. So frequencies that's high enough that coupling capacitor CC1 and CC2 and emitter high pass capacitor CE is on short, and with frequency that is low enough that the capacitance Sorry, I mean the transistor capacitance C mu and C pi are very large impedance. So an example is this one when you have common emitter amplifier with complex impedance ZT as a load, and usually ZT is parallel combination of RL and C. So you can have ZT equal to RZ parallel with impedance of L and impedance of C. So now let's analyze this RLC tuning circuit with the ZT as a load. So if I have this circuit here, for small signal, I can draw the equivalent circuit like this one, right? So basically everything up here is grounded. This RB here is the equivalent from R1 and R2. So R1 parallel R2, you can calculate that. So we can break down the ZT into RZ, parallel ZL, and parallel ZC. Okay, and these are just the impedance of the capacitance and the load inductance. And the actual load, the actual impedance of our load, or I would call impedance of the effective load, would be ZT parallel with RL. So as I promised, I don't want to get too deep into the math. Therefore, let me just try to summarize this in here. So if you want to find the amplifier voltage gain, of course you want to find the relationship between output VO and input VS, right? So all you need to do is find the relationship between an intermediate term, which is V pi. So you use your happy pi model. You can basically derive all of this until you have your gain equation. Okay, then this AB is in terms of S equal to negative GM over C, then R pi parallel RB over RS plus R pi parallel RB over S squared plus S squared multiply S multiplied by 1 over RZ parallel RL multiply C plus 1 over LC. Okay, this is very lengthy, but what I would tell you is this term, it looks like a band pass filter. Okay, it looks like a band pass, actually a mid pass filter. Sorry, yeah, band pass filter. Sorry again, with a gain. So what do we find next is we want to find we want to analyze something in this band pass filter. So if you look at the frequency term here, which is S, okay, it's in S domain, but you can plug J omega back in for S. What you see in here is when S go to 0, this whole terms will go to 0, right? When S go to 0, this whole term will basically go to 0. Therefore, gain is 0. So if S go to infinity, okay, this two term will be super large. That makes the denominator very large. Therefore, this big term go to 0 also. So for a very small frequency, this transfer function go to 0. For a very large frequency, this transfer function go to 0. Therefore, you can expect that, okay, so probably in the middle there's a resonant frequency. I will call that resonant frequency omega naught. Okay, so and the maximum gain probably at the resonant frequency. Okay, so so now if we know that this transfer function has the form of band pass filter, Okay, we put in the form for bandpass filter. So we're gonna cheat a little bit here. We figure out that bandpass filter looks like this. This is low frequency. Okay, gain go to 0. High frequency, gains go to 0. In the middle, they have a resonant frequency. So with this equation, you can actually matching with this form here. So as you see right now, let's compare. This transfer function doesn't have s squared, doesn't have any term for s squared, right? Just have one single s. So first of all, you can conclude a2 and a0 is 0, and you have a1 is this whole terms here. Next, it's easy to see that you have omega naught squared equal to 1 over LC. Just compare this denominator and this denominator. Not that difficult. If you have omega naught squared equal 1 over LC, then you can have omega naught equal to 1 over square root of LC. So now you know where is the resonant frequency. Next, what I want you to do is I want you to figure out what's the bandpass. And hint here, bandpass is actually this term omega naught over Q. So now you have the bandpass equal to 1 over RZ parallel RL multiplied by C. So here's the two important things that you want to take note. Okay, finally we want to find the gain, the midband gain. That means what's the magnitude of the transfer function at the resonant frequency. So we know what is the term for the resonant frequency. Technically, all we need to do is plug in. All we need to do is plug in the resonant frequency, then find the magnitude of it. Then at the end, you can have this is your gain. So if you have your so normally without the load, this GM is around 50, right? Okay, this GM is around 50. But if you have R pi parallel RB over RS plus R pi parallel RB, this is probably around this is 50 milli, so this is around maybe less than 1. So that gain is not very high normally. However, if you couple with your load resistance. So let's say if I have this one to be the whole thing to be 100 kilo ohms, then I can easily amplify it for 100 times, easy. So you can see that the magnitude, the maximum gain, midband, is a lot larger than 1. Okay, so we can have significant voltage gain as well as high and low frequency filtering. So that's why this one is called tuned amplifier, because you try to focus exactly right in the middle of the frequency that you're interested and amplify up at that point. Anywhere else you cut up. So quick summary in here. You know 3 important information, right? You know where is the resonant frequency, you know the bandwidth, and you know what is the midband gain. So I want you to basically maybe pause the video for a minute and just look at each term in each different equation here. For example, in the gain, you can see that L and C is not presenting in here. So if you build a tuned amplifier circuit, and you want your circuit to have the ability to maybe fix the gain but vary the frequency a little bit, then what you want to do is maybe when you build your tuning circuit, you want the RZ to be fixed. Uh, it should not be variable. So now you look at the bandwidth. Bandwidth, there's RZ and RL contributing to it, and there's C, but there's no L. Okay. So in the case that if you want to vary the bandwidth, you can change C. Okay, you can find a way to vary your capacitance. So either you can use a series of switches or a variable capacitance. That's one thing. Another thing is if you have this denominator is very large, you can effectively, if you have this denominator is very large, you can effectively have a very narrow bandwidth, so that you can tune very precise resonant frequency. And finally, for the resonant frequencies, you see that the only thing that basically you see that in the tuning circuit, RZ affect the bandwidth and the mid-band gain, so you want to keep it the same. The capacitance affect the bandwidth, so if you want to vary the bandwidth, you change the capacitance. If you don't want to vary the bandwidth, you keep it the same. If you want to vary the resonant frequency, you can vary the inductance while keeping everything the same. And if you see the image of an inductor in here, it's basically a metal coil. So you can easily design a device that varies or you can use a variable inductors. Just basically move the needle around so that you can tune your resonant frequency easily. So inductor is basically a metal coil that produces current going through. Therefore, internally your inductors actually consist of some series resistance also. So in order to accurately analyze the previous circuit, we actually have to take into account the series resistance of our inductor. To do so, we will have to find the equivalent circuit consisting of the ideal inductor with a parallel resistance. So here, if I have my inductor consisting of the raw inductance and a series resistance, I can have an equivalent circuit of ideal inductor with a parallel resistance. So here's the math for it. So if I call Vt is the effective impedance of this block here, so for a series circuit, it will consist of the impedance Rs, which is the series resistance, plus the impedance L prime. Therefore, I would have equal to Rs plus DL prime plus equal to Rs plus J omega L prime. And we have Rs series system, RL idealized inductance. So in the same way, we can actually represent this same Vt in the parallel form. in your Canvas module, you have an example of the tune amplifier, and in that example, you can see that you are given this circuit, the tune amplifier. You are asked to figure out what is the value for RZ, C, and L, so that you can tune this amplifier to a specific frequency with a specific bandwidth and gain. So that three component: frequency, resonant frequency, bandwidth, and gain. However, as we remember the equation of the gain, right? Mostly is affected by this component resistance RZ. Therefore, in this example here, what I want you to do is, now you have to take into effect the serial resistance of your inductor, convert that into the equivalent model, figure out what is RP. So here we have calculate RP. When you couple RP into this model, effectively you have changed your load resistance into RL parallel with RP. Therefore, in order to make the same gain, you need to readjust or recalculate your RZ in order to keep the circuit function as you wish for. So from the example in Canvas, if you want to make the gain to be negative 25, then you have the value of RZ parallel RL to be 50 kilo ohms. From here, you can calculate how much RZ you need. However, in this case, since you consider the parallel model of the inductor series resistance, you have to couple RP into the equation. That's why now you actually have RZ parallel with RL and parallel with RP. Set it equal to 50 kilo ohms. Okay, and because of that, you can notice now you have to adjust your RZ to be a higher number in order to keep the gain at negative 25. Instead of putting the tuning circuit at the load, you can also put the tuning circuit in form of only LC at the input. So as you can see in here, we have an impedance ZT, okay, the total impedance. We couple that to the input. So if you basically convert that to the equivalent circuit, we can have we can expand the ZT into C and L. If it's an LC circuit. For the L component, you want to break it down into L and RP, which is the parallel equivalent of from the serial resistance of the inductor. So to get the voltage gain, you do the same thing previously. So I'm just gonna skip through all of this. You go through all this math. You have some equation. You write that equation, and now you do some analysis on the final form of AV. As you can see, if I have the S go to 0, either if S go to 0 or S go to infinity, it's gonna go back to 0. And this form is actually exactly the same form with this form is exactly the same form with our the previous example when you have an RLC circuit at the load. And you remember what to do when you see that form. You actually take this number, use it to calculate the resonant frequency, because this one is equal to remember omega naught square, and this equal to your bandwidth. Therefore, you can have omega naught equal square root of LC, exactly the same with previous example, and your bandwidth is this whole group here. You can also plug in and consider, you can actually plug in omega naught, because now you have omega naught, you can actually plug in omega naught and consider what is the gain at omega naught. However, I'm just trying to skip it because as you can see at the end, the main source that dominates your gain is actually coming from RC and RL. So therefore, there's not much thing we can do in here to actually change the gain. So this type of circuit, you can tune the bandwidth and the resonant frequency instead of your voltage gain or amplification gain. So that's it for today. To sum up, let's see what did we learn today. We learned that by using reactive components such as capacitor and inductor, you can produce a narrow band or a tuned amplifier that basically allow the transmission to go through or to be amplified at the resonant frequency at LC, right? I mean the resonant frequency of the LC circuit. You can do two things. You can put your RLC at the load output, or you can put your LC circuit at the input. When you put the RLC circuit at the load output, you can basically allow transmission at resonant, but you can also tune your resonant frequency by changing L. Your bandwidth is depending on your choice of capacitor, but also the choice of your resistor. However, for me, I think that the resistance can be kept the same. Amplification is depend on the resistance at the load or the resistance that compose this ZT. When you couple the tune circuit, the tune LC circuit in the input, same you can get transmission at resonant frequency, and the bandwidth is going to be depending on the capacitor. Gain is very much not going to be considered because it's mostly contributed by the load capacitance. So that's it for today.
And this is the end of our lecture today. I hope you guys learned something new, and I will see you guys next time. Bye!